Dear students, today we will learn the design of Gantry Girder, which is an important design problem in the design of steel structures. So to introduce the Gantry Girders to you, they are the structures which are used in heavy industries and big labs for transporting the material or object from one place to another. So in this video, I'll be explaining this PDF, which includes the introduction part, the theory, as well as the problems. So first I will show you the picture of Gantry Girder to make it familiar to you. So this entire structure is used for material handling. Among these these alloy structures are called as the crane truss, CRANE, and okay, it is also called as crane bridges. There are numerous small detailings given in this figure. Don't want to know everything, but know the basic and the very important structures. So this machine part or this movable part is called as a crab, and the operation of this total structure is like this yellow element, which I told crane bridge or crane truss, is able to move in this length direction. It can be moved forward or it can be moved backward. Similarly, this crab can move along the crab bridge or crab truss, so that in a big room, any material placed at any point can be displaced to a desired location. And one more thing to note, it is not possible to operate simultaneously or to move simultaneously this crane truss as well as the trolley, only one at a time. And normally we will make this long beam, just I told crane bridge. It can be by a truss like arrangement or a beam like arrangement. Normally we will go for a truss like member, and here shown it is a beam member. And these last beams you can see at both the edges are called as the gantry girders, and these gantry girders will be supported on the columns. There will be numerous columns in a room, and in between two columns, it means the gantry girder is continuous, and the a span is taken between two columns. So we are supposed to design this gantry girder for this arrangement. So just to introduce that, the different loads acting on this gantry girder, it includes the weight of this alloy element, the crane truss, weight of the crab, of course, and in addition to these dead loads, there are loads like due to the movement of this alloy element to and fro, backward and forward, there will be a longitudinal thrust on the gantry girder. Also, due to the movement of this crab along the length of the bridge girder, there will be a lateral thrust on the gantry girder. So this additional longitudinal lateral thrust and these heavy loadings are making the gantry girder design a challenging one. So these are operated by a radio control, and there are so many other minute detailing. We'll just see it is like there's a hook which is supported to the crab for like lifting the material and keeping it to another point, and the wire rope will be there to support the load. Pendant cable, pendant uh, festoon, trolley festoon. These are minor details we don't want to understand for a structural engineer. Yeah, so there will be a rail over the gantry girder to facilitate the easy movement of this bridge girder, and also will be rails over the crab for facilitating the movement. Yeah, so these are the details which we need to know. And yeah, so this was the right figure shows a like truss crane which was telling that means the long beam can be made from truss also. Okay, and I'll show you a real picture of gantry girder which I'm looking into. Yeah, this can be treated as so. So these are called as main crane bridges, and I told supported on the columns on the left side, right? So this between these two columns, it is a span of the gantry girder. So these are some other types of photos, other views, photos for the arrangement that is bridge crane bridge. Yeah, so you can explore by yourself by typing Gantry Girder into the Google, and you can see different photographs uh, for getting familiar with the Gantry Girder. Okay, so coming back, so in this PPT or this PDF, we have the introduction part and then the different components of a crane system, which you will be familiar now, and the different forces like the vertical forces, dead load, live load, horizontal forces, fatigue effect, which will come on the gantry girder, which is very important uh, theory part. Then the impact factors and some different forms of gantry girders, crane columns, then how to design a gantry girder. Means the beam element which is supported on the column. So the loadings, as I told, the loadings makes it the design a challenging one. And in the introduction part is tell regarding there are two types of gantry girders. One is a manually operated traveling cranes, and the other one is EOT crane is the electrically operated overhead traveling crane. So when a question papers it may be typed MOT, manually operated, and EOT, electrically operated. So it doesn't uh, differ much in the for the structural engineer. It's only mechanical part. And in this PDF, we will learn understand the behavior of gantry girders to compute the different loads acting on the gantry girder, compute the maximum bending moment and the maximum shear force, which we discussed. Like they're subjected to lateral as well as longitudinal additional stresses, which makes these calculations and a challenging one. And to choose the suitable cross sections of the gantry girder and to design the suitable connections, which is with the last two portions is covered in the case of or in the class of design of steel structures. So we are supposed to study or concentrate mainly on to find the bending moment and the shear force due to this particular loading conditions. So this is now it will be easily readable by you that we have the column here on the left side, which is a stepped column. Stepped column means the column width is varying as the height is increasing, and the this is called as the gantry girder. Sorry, yeah. This is called as the gantry girder, and upon this gantry girder, the wheels of the crane bridge is located, and this is called as this is the crab girder or the sorry this is the yeah crane bridge or crab girder, and this small portion or this um, structure or object is called as a crab or trolley, and we have the hoist for lifting and placing the objects. This is the top view. We have the span of gantry girder from center of column to center of column. Then there will be two parallel crab girders upon which the crab is positioned. And so yeah, one more thing to note is a wheelbase, which is a span between two crab girders, and this wheelbase is actually positioned on the gantry girder. And in a very basic way, there are four components. One is a hoist, which is this portion to lift and to displace or to place the material at a different point. Hoist, okay. Then crane, crab or trolley, which is this object which you can move over the crab girder. And the third one is a crane truss or crane girder. So this portion. And the last one is the gantry girder, which we have to design based on the loading conditions. So you can read through this basic theory part. That means it is telling about what is the need of a trolley of crab. It can move in the transverse direction, and the crane bridge it can move in the longitudinal direction, which we discussed. And these are the different forms of gantry girders. It will be a big I section with the additional plate over the top and with the channel section. So this will increase the capacity of the sections. So the different forces acting on the gantry girder. So as the movement of the crab crane, there will be a longitudinal thrust on the gantry girder. So the gantry girder is from here to here. Treat this as a column. This vertical line is a column. And wheelbase, what we discussed is the distance between two adjacent crane bridges. And there will be longitudinal thrust due to the movement of the crane bridge. There will be vertical load at 2 points of span. For the span is the wheelbase, and we'll be having a lateral force due to the movement of the crab over the crane bridge. So those are discussed here. Vertical reaction from the loads of crane girder, longitudinal forces due to the starting and stopping of the crane, lateral forces due to the starting or stopping of the crane. Then there are some other factors or other forces like fatigue effect and impact effect, which we can take accordingly. So the vertical forces are described here: the self weight of the gantry girder, the load from the crane bridge as well as the crab, and the material weight which you will lift for the purpose, and the horizontal forces with the movement of the crane bridge as well as the movement of the crab trolley. Those forces are acting on it, and there will be fatigue effect due to the continuous movement of the material or the crabs. Then surely impact loading will be there because of the quick action of the gantry girder. The loads transferred are momentary. So when you lift the material as well as you are starting and moving the crab or trolley, there will be impact which is additional to the acting loads. So the impact loads it differs for the EOT cranes and MOT cranes. MOT cranes are manually operated, having a 10% only increased additional load. EOT have a more additional 25%. And the horizontal forces are given in a thumb rule wise. For EOT cranes, it is a 10% of the weight of the crab and the weight lifted. Weight of crab and weight lifted. Okay. And MOT is 5% manually operated. And longitudinal force is taken as 4% of the static wheel load. So these are the guidelines for selecting or to find the horizontal like the lateral loads as well as the longitudinal forces. So the gantry girders are designed according to the steel design code, and we will directly get into the problem to understand the general design guidelines. And there are some limiting deflection values for the gantry girder, like for a steel beam. There is MOT cranes, it should not be more than L by 500. For UOT cranes up to 500, L by 750, above 500, it should be less than L by 1000. So those things has to be taken care of while designing for serviceability conditions. We just see in the different forms of gantry girder. This may be as for the examination's point of view. So there are different types of crane columns. The crane columns are the columns which will support the gantry girders, and generally it can be divided into light duty crane girder, medium duty crane girders, and heavy duty crane girders. Depends on the uh, weight of the gantry girder and the other things. So you can see here the different arrangements, the column, there is a this overhang. This is actually not a stepped column. The column is attached. A such element is attached to the main column. It is bolted, and upon which the candidate is positioned. And this is actually a side by side two columns. This is actually a stepped column. The different arrangements, which we're not looking into this in this video. And then the preliminary choices are normally for a MOT crane, manual operated cranes will go for I section. For as the span is increasing, we go for I section to I section with plates or channel at the top. Then a plate girder, which is a very high web, and for the large span, we'll go for the box section. These are the general uh, guidelines which are followed by the industries based on the capacity of the crane. What are the other values of uh, distances, wheelbase, weight of crane, all the things are detailed here. So in the problem to solve, you will be given all these values. Okay. So the design procedure for the gantry girders, which is our topic, includes the first one is to find the maximum wheel load. So the maximum wheel load is the load which includes the weight of the big crane bridge, then the crab trolley, then the lifting weight, and all those things will come under the maximum wheel load. So this occurs when the crab is closest to the gantry girder, and the maximum wheel load will be half the reaction of the two wheels of the crab and the impact load. So this will be the first calculation, maximum wheel load. Second one is to find the maximum bending moment due to the vertical forces. Third step, to find the maximum shear force due to the vertical loading. So this figure shows that so this AB is the gantry girder, and this W are the weight from the crane bridge on a wheel base of A distance. And by the structural analysis, we can find the maximum bending moment as well as the maximum shear force for this arrangement. And after finding the maximum bending moment, maximum shear force, we were supposed to design the gantry girder, design this AB element for these loads. Then to find the section modulus required uh, by knowing the moment acting on the beam gantry girder and the bending stresses, then finding after we get the section modulus, we can find the IXS and IYY required, and then we will give a section. Then the step 7 is on the lateral forces, which is the force contributed by the crab trolley movement, and the calculations for that. Then step 10, step 9 is the checks of QBC permissible from the IS 800 tables. Then step 10, there are the checks thereafter. That is for the bending biaxial check, then longitudinal force check, shear check, diagonal buckling, deflection, connection. So this we'll see while doing the problem. Okay, we'll see that. 10.10 design examples. Example 10.1. A hand operated 50 kilonewton overhead crane is provided in a workshop. The details are given below. Center to center distance between the gantry girders is 16 meter. So that means center to center distance between gantry girder means it is the total length of the crane bridge. Span of the gantry girder is 6 meter. Weight of the crane is 40 kilonewton. The wheel base is 3 meter. Weight of the crab, the topmost portion or object is called is 10 kilonewton. Maximum edge distance is 1 meter. That means this is actually this LR is the gantry girder, and edge distance 1 meter means the wheelbase can't move to the last 1 meter. Okay, it is only moving only between these 2 points. Okay, so design a sibly supported gantry girder, assuming the flanges are laterally supported. So solution is like this. We have the weight of the crane 40 kilonewton. So the weight of the crane is provided as UDL 40 kilonewton per meter. Then we have the hand operated 50 kilonewton overhead crane. So we have yeah. So the weight of the crane we know 40 kilonewton, and overhead crane we have 50 kilonewton. Then we have the weight of the crab 10 kilonewton. So by representing the loads on a gantry girder LR, there is a edge distance 1 meter on both sides, and this is the self weight, and the overhead crane weight plus the crab weight is 50 plus 10, 60 kilonewton, and we know the center to center distance between gantry girder 16 meter. Yeah, so we have to lift a load of 50 kilonewton. So the 50 kilonewton plus 10 will be the weight of the crab, and 40 will be the UDL for the crane bridge. So to find the maximum wheel load, we are loading all these weights to the crane bridge, and uh, at a distance of this maximum distance, To find the maximum maximum weight load by taking the moment about the R, this UDL 40 into total L by 2 minus 16, so 60 into this detecting the at distance 15 plus RL into 16 will give you the maximum wheel load as 76.25. So at this L point we have two wheels, so each wheel will have a load of by 2 38.125. Then we are loading this load to the gantry girder in the second stage. So the maximum bending moment due to the vertical load. So the span changes to the gantry girder span 6 meter, and assuming a self weight for the gantry girder as 1 kilonewton per meter, and the bending moment due to the dead load it is W squared by 8 1 into 6 square by 8 by self weight 4.5 kilonewton meter. And also from the figure we have uh, the calculations for finding the uh, to obtain the maximum bending moment, we have to place the load and resultant should be placed at the equidistant from the midspan like this, from the center of the gantry girder, and we obtained figure like this. So we have the AB as the gantry girder length, 38.125 are the wheel load. So this is the midpoint, and by locating like this, we will get the bending moment due to the load B load as 64.32 kilonewton meter. It was by taking the moment about the B, the rightmost point, with all these loads included, and we have seen in the previous uh, table that the impact load how to take. All right, this is showing that. Yeah, so these are about the vertical and horizontal loads, and the impact load has to be taken 10 percentage. So coming back to the problem, so the an additional impact load of 10 percentage has to be taken to that. So 64.32 plus 10 percentage 6.43 will give you the moment. So M1 plus M2 plus M3. So M1 was the initial bending moment with the self weight of the gantry girder. 64.32 is the actual bending moment, and this extra 6.43 is due to the impact loading, impact conditions. Then the calculation step 3, to find the maximum shear force, we have WL by 2, which will give you 3 kilonewton. And for maximum shear force due to the wheel loads, one of the wheels should be near to the support. So this is actually near to the support. Okay, to the maximum shear force. So then, based on this arrangement, you can find the shear force to get a value of 57.19 kilonewton. For this also the impact load is taken as 10% of the maximum wheel load, which will be 57 was the correct value plus 10 percentage. For high point 72 is the 10 percentage value, which will add to 65.9, where 3 was the value due to the self weight. So 65.9 will be the total shear force acting on the gantry girder. And so now we found the different bending moment shear force which will act on the gantry girder, and the rest is the design of the gantry girder, the steel beam element. So first is the calculation of the Z required. So the Yield strength is assumed as 20 to 50 megapascal and sigma BC is equal to 0.66 into Fy. I'm not telling this minute details or showing it in the code as you have already did the steel course. So we have the sigma BC of 165. So is it required is total bending moment divided by sigma BC will give you. So you are in need of 456 into 10 power 3 mm cube section modulus uh, section having a section modulus of this mesh value, and we can take from the IS table. This ISMB 350 at 524 Newton per meter is satisfying the conditions of is having 778 over 5456, very high value. These are the IXS IYY different breadth as well as the total area of the cross section, and we can find the sigma BCS and sigma BTS is equal to mx by Iyy into y. So which will give you bending moment by axis into y will be total depth is 350 by 2, which will give you 96.6 Newton per mm square. Due to symmetry, both the values are same. The tension maximum stress and compression maximum stress, which is less, it should be less than 1.1 times the 0.66 into Fy. So those condition is satisfied. Then we have seen just in the previous table how to find the lateral load for the manually operated is 5%. So 5% of trolley weight plus weight lifted 10 plus 50 3 kilonewton. So we can consider this lateral load to the the total lateral load is 3 kilonewton, and we have four wheels. So divided by 4 will give you 0.75. And the maximum bending moments and the shear force can be calculated by the proportion method. Mi is equal to mq into lateral load by maximum wheel load. We have the lateral load as 0.75. Maximum wheel load we have found initially as 38.125 without the 10% extra for impact. So those calculations will give you 1.625 as additional, not additional, it's the extra. It is a bending moment offered or the it is produced on the gantry girder by this lateral force, and similarly the lateral shear force is given by V2 into lateral load by maximum wheel load. We'll get 1.125, and the maximum compressive stress due to the lateral loads we can find like this. So previously we have calculated in the vertical, listen the pure bending in the uh, no, like the normal bending, but now we are into the lateral bending. So that's why there is a we are taking b by 2 to find the compressive stress and the bending stress. So m by Iyy into b by 2 will give you the maximum compressive stress as 32.9 Newton per mm square, and the permissible value is 0.66 into Fy. So we can check for the bending stress. The first one is for the longitudinal bending. Right, I'm telling about that is suppose the gantry girder, it will bend this in this way, and this bending moment is actually 96.6, and it's in the top view. Due to the load, it will also bend in this way. It's in top view, uh, plan view, not plan view. This is a side view. Okay, so this combination effect is checked and it is found less than 1, so it's okay. Then the longitudinal loads, we know that for manual operator is 5% of the maximum static wheel load, which will give 1.9, and that will act along the length of the gantry girder, and assuming that so the uh, rails are placed over the gantry girder, and we know that longitudinal loads are acting in line with the gantry girder. So the longitudinal force will create a moment to the gantry girder. Find that, let's assume that the height of the rail is 75 mm. This is 75 mm rail, and we have the total depth of the beam is 350. Half will be uh, it will be but 175, and we can find the bending moment about the cross section. Find the maximum compressive stress is given by 0.89, which is less than 1.1 times the zero point 0.6 into Fy. And next is the check on shear. The average shear stress is given by 65.9 into 10 power 3 pi, the cross section area, and the value. And the value should be less than 1.1 times the 0.44 into Fy as per the steel design IS 800. This is a check for deflection. We have seen in the previous table that there are different deflection limits for different types of cranes and the loading. And for this case, manual operated, it is for by L by 500, and by the same for the like the moment we are positioning the loads to get the maximum deflection, and the calculations for the deflection of mid span, which is a contribution of every load by the method of superposition, will give you a deflection as 8.65, which is less than 12 mm. So the Gantry girder proposed is safe for the deflection. So I will stop for today. Thank you.